Thermochemical Changes, Chapter 10, Theories of Energy and Chemical Changes. In this next section, we are going to explore ways to calculate theoretical amounts of energy released or absorbed by chemical reactions using thermochemical equations. We will also look at the concept of energy efficiency and the effects of Canada's dependence on fossil fuels. Hess's Law. Before I get into the details of Hess's Law, I want you to consider something. This is a potential energy diagram showing the change in enthalpy during the formation of carbon dioxide from its elements. For every mole of carbon dioxide produced, 393.5 kilojoules of energy is released. For comparison, this potential energy diagram shows the production of carbon dioxide as a two-step process. Carbon monoxide formed from its elements, then carbon dioxide produced by reacting the carbon monoxide with more oxygen. The energy released at each step is indicated. But what's interesting is the sum of the reactions produces the same net change in enthalpy as the single-step reaction. Your textbook uses the example of two cyclists making their way down a hilltop, and appropriately concludes that while cyclist B will reach the finishing point first, the net change in potential energy is dependent on the height of the hill and not on the path taken to traverse it. So whether you're using one process or a number of processes, the net change in enthalpy is dependent on the overall process rather than the number of processes. So this is the essence of Hess's law, and is stated as follows. The enthalpy change of a physical or chemical process depends only on the initial and final states. The enthalpy change of the overall process is the sum of the enthalpy changes of its individual steps. Experimentally, this process has been shown to work. This is therefore a useful tool in determining the enthalpy changes for processes that are difficult to conduct experimentally, such as very, very slow reactions or extremely explosive reactions. We can apply Hess's law using experimentally determined values to calculate the theoretical energies of these other processes. Let's apply this to an example. Iron metal can be obtained by the reaction of iron 3 oxide and carbon monoxide gas as shown here. Determine the enthalpy change for this reaction given the following information. Now adding the two equations as shown will not yield the reaction of iron 3 oxide with carbon monoxide. As you can see from the equations, the iron 3 oxide is a reactant in the net equation and a product in one of the given equations. So simply adding up the delta H's as it stands is not going to give us what we want. As is frequently the case with Hess's law questions, you will need to manipulate the given equations before adding them to get the required net equation, also called the target equation. There are two ways to manipulate equations. First, you can flip it, so reactants become products and products become reactants. And second, multiply the coefficients by a factor that changes the mole amounts of the reactants and products. By looking at the given equations, we'll see what needs to be done so they'll add up to the required target equation. Compare equation 1 with the target equation. Equation 1 does include carbon monoxide and carbon dioxide molecules in the target equation, but there's no oxygen in the target equation. At this moment, I'm not going to let it concern me because commonly occurring molecules like oxygen and water are likely to be found in more than one chemical reaction and ultimately find themselves at the end of our equation manipulations as both reactants and products, in which case we can reduce this redundancy by cancelling or removing equal quantities from each side of the equation. The target equation has those carbon molecules with a molar coefficient of 3. To make equation 1 have the same coefficients, we'll multiply each component by 3. Since we're tripling the amounts of the reactants and products, then the enthalpy change for the reaction will also triple. Comparing the second given equation to the target equation, I can see that the correct coefficients match up with the important players in the target equation, but the equation needs to be flipped to get the iron metal as a product and the iron 3 oxide as a reactant. What do we do about the change in enthalpy? Well, recall that if energy is required to make a reaction proceed to products, then the exact same amount of energy is released if those products are reformed back into reactants. In the case here, equation 2 shows that iron metal reacts with oxygen in an exothermic formation reaction. If we flip the equation, the reaction becomes a simple decomposition endothermic reaction by the same magnitude. By adding together the two manipulated equations as well as their delta H's, and cancelling components appearing both as a reactant and a product, we end up with our required target equation with its enthalpy change. This one was fairly straightforward as there are only two given equations. Variations of this type of question can include more equations, including one that isn't even used at all, just to mess with you. Equations that need to be flipped and multiplied, and even equations that simply change one phase to another, like water to steam. That simple equation has its own delta H, therefore state must be considered with all Hess's law problems.